This is my assignment for computer vision. Assignment for computer vision. I'm called Scenographer. This is my registration number. Now the first slide is about edge detection, and edge detection is simply the significant change in the discontinuity or color within an image. So that disparity brings what we call the edge detection. Detection can be edges. Not every detection edges. Any edge is about the disparity or discontinuity in the intensity or color in an image. So that imbalance brings about what we call an edge. An edge can be detected using the vertical or horizontal masks or filters, and they can be used to detect images with respect to those respective directions of horizontal and vertical. These are the pictorial that shows a transformed image whereby the edges are reflecting. So the process of multiplying pixels with the image portion, pixels from the image portion is what we with the mask is what we call convolution. So you add the total after computing to convolving. So that value is replaced with the center pixel from the image. Now, detection is all about the process of identifying objects or people or text or actions that are happening within an image or a video. Like you see this diagram here. This diagram here shows some information being detected from that picture, and this the information that these cars are being enclosed by what we call bounding boxes, means that they are being detected successfully. Also, they are called labeled tags. How does image detection work? Image detection works following a number of steps. There's data collecting data from various sources, and that data is pre-labeled and then fed into the machine. And there is what we call pre-processing of data. Pre-processing of data happens when you decide to do some data cleaning or smoothing of the image so that you can easily detect. For example, if you want to detect the edges from an image, you can use the Gaussian smoothing as the pre-processing task. Then there's feature selection. Feature selection is about generating or finding out or extracting the key features within an image, like edges, corners. Then there's localization. Localization is about enclosing the objects or sections within an image or a video that you want to trace or to detect using the bounding boxes. Then there is what we call classification. Classification is about segmentation. It's about segmentation and categorizing of the input pictures, such that the machine can learn and then performs the classification, just like from this diagram here. We have input dogs and cats, and then at the end of the day, the machine has to segment and then does the classification. Then there are methods of edge detection. There is Sobel, Prewitt and Robert, these are gradient-based. And then there are Gaussian-based methods. There is Kane edges and Laplacian of Gaussian. Sobel uses a 3x3 Kano matrix. There are two masks. There is the horizontal mask and the vertical mask. The horizontal mask is used to detect edges relative to the horizontal axis. And then the vertical mask is used to detect edges relative to the vertical axis. And then the gradients are computed respectively. And then after the magnitude is computed, now this value here will replace the center pixel from the image. And this is the detailed method. The detailed approach used to detect edges. So this is Sobel operator. This is the image portion. So this image portion will be convolved with the vertical mask or even the horizontal mask, and then the values are computed, as you can see, Gx and Gy, and then this Gx and Gy, we compute Xt, or we compute the magnitude. Now it is this value here which we get that will replace the center pixel from the image portion. Now this table here shows the successful convolving, because this image portion or this marking here will keep on shifting from one portion to another until all the pixels are exhausted from this diagram. Prewitt works in the same way like Sobel, but now the difference is that the filter or mask that changes, but the principle remains the same. Then there is Laplacian of Gaussian. Laplacian of Gaussian is now the second derivative. The other one, the other three, the gradient-based uses the first derivative to detect edges in the image. So this formula here shows the second derivative of an image with respect to the x component, then the second derivative of an image with respect to the y component. And then this method, this formula here is applied to the image, and then the edges are detected. But before the edges are being detected, they need to perform a Gaussian smoothing so that we can eliminate the noise from the image. This is a picture that shows the Gaussian the Laplacian of Gaussian. As you can see, the final image is being detected here. Let me try to do some screenshot. So this was a question in assignment. It was about to detect an image using a number of parameters following this function. And this is the code for the successful implementation, the Python code to detect edges. So as you can see from this photo here of Lina, this is the input and this is the output. Here you see that the edges have been detected. So I imported libraries, matplotlib, and then OpenCV, and then I applied the Gaussian smoothing, and then I supplied sigma scalar quantity or parameter of 1.5. There's what called corner detection. Corner detection, it is it's all about the intersection of edges. When the edges intersect, we form what we call a corner. So you need to first perform the intersection of edges, then you reach to what we call a corner. A corner exists in that at that spot. So where there is change in the intensity of an image abruptly in several directions, brings to us what we call a corner. So a corner, how do we detect corners in an image? So a corner, of course, as I've said, it is detected when the two or more edges meet. When the edges meet, then a corner will be could be. And it is useful it helps us to identify essential image points or our points of interest within an image so that you can use them for a number of tasks like image recognition, motion tracking, and so on. Roles of corner detection helps in feature detection and matching, image registration, object detection and tracking, calibration and 3D reconstruction. Calibration is all about estimating the intrinsic and extrinsic parameters of an image so that you can generate or come up with an accurate image or a video within the 3D space or the geometry scene. So, and corners help us to perform that task. Now, how are corners detected? Corners are detected at the spot where the two edges meet. So, the rapid change in the intensity in two or more directions forms what we call a corner. So, corners are detected by computing the magnitude of the image with respect to the x component and also computing the magnitude of an image with respect to the y component, as you see from this formula here. These are the various corner detection approaches. There are quite many, but I came up with those few. There is what we call Harris corner detection algorithm. Harris corner detection algorithm relies or computes the magnitude of small variation of points occurring in all directions, and therefore detecting corners within an image. So it uses the function of autocorrelation to compute the corner score with respect to direction. And the problem with this Harris corner detection algorithm, this one suffers or it is susceptible to noise. It can be distorted by noise. Because of that pitfall, then there was invention of what we call the Sky-Thomas corner detection algorithm. This one it computes the minimum value of two eigenvalues, and it computes the gradient of the pixels or of the points using the Sobel operator, using the Sobel operator. So it computes the gradients of the image using the Sobel operator. Then there's what we call future from accelerated segment test. Now this one examines a circle of pixel surrounding the center pixel so that a corner can be detected based on distribution of intensity surrounding that pixel. So as you see from this diagram, there are pixels here, a pool of pixels surrounding the center pixel. This center pixel here is the one that it determines whether it is a corner or not. As you can see from here, even here, the center pixel. So it works by examining center pixels around the central pixel and determine if the center pixel is a corner or not. Now there's this part of the question, it was within the assignment, it was about how transform and parameterization. So this it was all about Hawk transform is about the matching. It's about matching of the points or mapping the points from the XY coordinate system or the Cartesian coordinate system to the polar, to the polar coordinate system, or the how this word how transform, or I can call it the parameter space. So this equation here is an emulation of the normal equation of the line, but it has been parameterized. It is expressed in the parameter space. In the parameter space, but it is emulation of the other normal equation of the line y equals to mx plus c in an y coordinate system. And here we are applying the values of xi and yi. The same, but just here we are appending values of x within this equation here. Then when we multiply this, because we are after calculating the amplitude and the phase of the sine wave or the sinusoid curve. So when we multiply by the origin, the value of the origin. When we multiply and then divide it by multiply this equation and then divide it by this, we shall get this block of the equation here. Then from trigonometry, we know that sine alpha times cos alpha and times sine theta. Then you multiply by the origin, you'll get the rho. So this is the sine alpha is equal to that. Cos theta is also equal to that. Now when we add these two, we shall get this sine theta, sine of alpha plus theta. Then this origin here, we shall replace it by a constant b. When we replace it by a constant b, and that constant, that one will be our amplitude. So it will be our amplitude of the sine wave, and this alpha here, it will be our phase. Transform parameterization. So, okay, this question was about why do we parameterize instead of why don't you stick to MC or CM coordinate system? Because of this pitfall here. The slope of the XY coordinate system is between negative infinity to positive infinity, and the accumulator is too large to accumulate the values and requires a lot of memory for computation. And the orientation is infinite for polar-based coordinate systems is finite. What does that one mean? It is infinite. It is infinite in such a way that the value of theta lies between 0 and pi, and it is this contradicts sharply with the other, which the infinity, because this one lies between negative infinity to positive infinity. It is contrasting sharply. This was also another question from the assignment. It was about to relate the two equations from the Hughes transform or the polar coordinate system or the parameter space and the XY or PM coordinate system. When we relate the two equations, we come with this. That's why you see our intercept is 0 over sine theta, and then the cos, the m, these are the gradient. The gradient is that one. So you extract, you just relate it to the normal equation of the line from the XY coordinate system. and then you come up with this value here. Now, this question here, it was about us to plot points on the such that we generate the sinusoid curves. So these are the points 10, 10, 20, and 30, 30. So this is their constituent, the constituent sinusoid curves. In the Hue transform space, or in the I normally find it easy when I call it the parameter space. So the value of theta, or the point of intersection, the Hue space 28.2, and then the theta is 0.79. Now the slope is 0.98, and the y-intercept is 39.6. So this is the equation where these values are being extracted from the value of the gradient and the value of the y-intercept from the XY coordinate system. Now this is the Python implementation of this slide, the Python implementation. Then convolution, it's all about getting the portion of the image and then multiplying it or invoking it with the filter, and then you get the value of the convoluted value. That convoluted value replaces the center pixel from the image, and then the edge is so here we are filtering. This is the original image, and here we are filtering the image. And this is the Python implementation. It was the question within the assignment, and this is Python implementation of that code. Now this one was detecting the edge. It was also a question within the assignment. This is the input image, and this is the image that whose edges have been detected using parameters. It's in a value of image using this function edge detection, and these are the libraries I've used. And before we apply, we had to apply the Gaussian filter so that we can remove the noise, intrinsic noise from the image. And then we applied a sigma scalar quantity or value of 1.5 to the image. This is what I came up with from the implementation. So that's the end of my presentation. I've been rushing because of the time. That's my presentation. Thank you, Doctor.